If there are impairments in the liver, that's when we can start to see problems with any substrate, whether it's glucose, whether it's fructose, whether it's alcohol, whether it's fatty acids, whether it's amino acids. If the mitochondria are not effectively converting that substrate into energy, and that's a very sensitive process. If there's oxidative stress, if there are nutrient deficiencies, if there are other factors that we'll talk through here in a moment, it will mean that the amount of substrate that can be utilized in the mitochondria decreases, and there will be more fat production there. But that doesn't mean the substrate caused it. The glucose didn't cause it, but the alcohol definitely can cause it due to the acetaldehyde production, due to the endotoxin production in the digestive tract, and some other unique aspects of ethanol. So the ethanol itself can actually cause that, whereas the glucose and fructose don't have inherent pathways that drive that. Now, there is a bit of a caveat here that I'll get to, which has to do with how a lot of research is done looking at the effects of fructose at the liver. And there's two issues here. So, well, there's a few issues, but this first one, in the vast majority of studies that are done on rodents, which is most of them, most of the studies are done on rodents, they're given pure fructose as a very large portion of their total calories. Now, our digestive tracts and rat digestive tracts don't absorb pure fructose very well. And that makes sense because in nature, we never get pure fructose. Anytime we get a food that has fructose in it, it's balanced out with glucose, and the glucose helps with the absorption of fructose in the intestines. When we don't digest and absorb that fructose, whether it's us or rats, given pure fructose, the fructose then doesn't get absorbed. It doesn't actually go to the liver. Of course, a portion will, but a large portion doesn't. It goes down, it feeds bacteria. Those bacteria produce various toxic things, including lipopolysaccharide or endotoxin, which then gets absorbed, goes to the liver. I mean, it causes intestinal permeability, gets absorbed, goes to the liver, and is massively toxic there. Actually, something that's toxic there actually causes massive inflammatory effects, directly interferes with mitochondrial production, and causes a number of other problematic effects. And so when you have a study where you intentionally or unintentionally create massive endotoxin issues and then provide a substrate like fructose, you're going to see a large amount of it go to fat. Same with fatty acids, same with glucose. If you have a large amount of endotoxin and then you provide substrate, you're going to see liver fat accumulation. And that's what happens in these studies looking at rats, looking at apes, looking at humans, where they provide pure fructose. There are studies where they provide antibiotics to clear out bacteria so there's no endotoxin production, and it prevents the inflammatory effects of the fructose. It prevents the fat accumulation from the fructose. So we know that one of the main issues, one of the main reasons why you might see increased inflammatory processes and increased fat accumulation in the case of pure fructose dosing in poorly designed studies on rodents and on humans and on apes is due to this bacterial endotoxin issue, which is, of course, not at all accounted for here. And if you were to just look at the bottom line, the conclusion of those studies that say fructose causes fat production in the liver and it causes inflammation at the liver, you might come away with a diagram like the one that Robert Lustig showed here, but it is not accounting for this massive issue of endotoxin. Another example here, and I'm just going to touch on these briefly. I'll be citing the studies in the notes as we have talked about these before, but polyunsaturated fats are another major driver of liver inflammation, of fatty liver disease, and rodent diets are very high in polyunsaturated fats. Human diets are very high in polyunsaturated fats. That's what all the seed oil talk is about. They're basically one of the highest sources of polyunsaturated fats. And there are studies showing that if certain compounds are used to block the metabolites of PUFA, to block the downstream products of polyunsaturated fats that cause inflammation and cause oxidative stress, that also prevents the inflammatory effects of fructose and the fat production from fructose. Even when the same fructose is provided, but we block the effects of the polyunsaturated fats, we don't see those issues with the fructose. So again, two primary drivers here of fatty liver disease that are totally independent of the fructose, but are often blamed on the fructose. We also have the fact that rats are an extremely poor model for studying liver de novo lipogenesis from fructose. There are studies looking at the enzyme levels in human livers versus rat livers and what compartments they're contained in and how each type of liver utilizes fructose or any substrate. And they basically show that rats don't utilize the fructose as well, and they're much more likely to produce fat in the liver. So when we look at these rodent studies showing that fructose is causing fat production, even if we account for the endotoxin and PUFA, we're still going to see greater rates of de novo lipogenesis, greater rates of fat production, which is just because of the fact that our human livers are far more efficient at utilizing fructose than the rats, and that these rats have generally poor metabolic state or generally in a poor place metabolically to be able to use the fructose. So it's just a feature of that, and it's not actually something that we can translate to humans and human livers. So these are a few of the primary reasons why we might actually see some of the problems that could happen with fructose in research, but they're not actually due to the fructose itself. Now, I also have to make another caveat here, which is that if you provide incredibly high doses of fructose, like, that study we were talking about earlier, 270 grams, there are many other studies that use massive amounts of fructose, 25%, 30%, 50% of total calories. Sometimes they'll take the total amount of calories and add an extra, they'll do an overfeeding study where they add another 30% of total calories just from fructose. Typically, they do this in metabolically unhealthy people. When you do those kinds of things, you can see overload at the liver. You can see fat production at the liver. You can see inflammation at the liver. You can see uric acid production at the liver. And we talked about this in that uric acid episode, which was episodes 84 and 85. But this is totally irrelevant to metabolically healthy people eating lots of fructose, or even metabolically unhealthy people eating typical amounts of fructose, because the amounts that they're providing are in massive quantities. Typically, they're overfeeding and have all sorts of other aspects of the study. So, we talked about this in the uric acid series, where in a couple of studies, in one set of studies, in order to see increased uric acid, they had to feed pure fructose at 35% excess calories, and they had to restrict movement and exercise to the point that the participants were only allowed to do 1 hour of leisurely exercise a week. That was the type of protocol they had to use to actually see increased uric acid. They had to see you eat your full day of calories, then you add an extra 35% of pure fructose sweetened beverages, or some other form. I think it was fructose sweetened beverages, in order to see any amount of increased uric acid. And you're not allowed to exercise or even just, do leisurely activity more than an hour a week, because that would prevent this effect. And then in other studies, they would feed pure fructose sweetened beverages at 25% of the total calories someone's consuming in overweight people and obese people who have some level of metabolic dysfunction. And then you can see some increase in uric acid. So the types of studies that are suggesting that fructose increases uric acid or de novo lipogenesis to any significant amount or inflammatory states are based on really faulty protocols that are not at all accounting for the nuances of fructose digestion, absorption, and metabolism. So it's worth touching on all those things very briefly, and we're going to go through a study here looking at an example of how much fat is actually produced from fructose. And in this idea that Robert Lustig is putting forth, that fructose is inherently toxic, it's inherently a poison, in contrast to glucose, which is totally fine. It's the energy of life. Fructose is a poison, glucose is fine. We're going to look at a study here comparing the consumption of glucose and fructose, and if it actually increases liver fat production. Now, we could use this as an example or as a marker of whether everything else is happening in this diagram that Robert Lustig has, because all of it is dependent on that excess fructose going to the mitochondria, producing liver fat, that driving inflammation. If we're not seeing the liver fat, we know this is not happening. So we'll take a look at this study titled De Novo Lipogenesis During Controlled Overfeeding with Sucrose or Glucose in Lean and Obese Women. So again, we have an overfeeding study. This is the type of thing you have to do if you want to actually see de novo lipogenesis in an appreciable amount. And if we were assuming that Robert Lustig was correct and that fructose is a poison and it's uniquely fattening, uniquely inflammatory in the liver, it's very different from glucose, we would expect that, especially in an overfeeding study like this, that with the sucrose group, which is table sugar, half fructose, half glucose, we would see far more de novo lipogenesis than in the glucose group, just pure glucose, no extra fructose there. And so we can take a look at what they did here. They state, and their conclusion, where they state firstly that de novo lipogenesis was measured during 96 hours of overfeeding by 50%. 50% of total calories. So if someone is eating a 3,000 calorie diet, they bumped them up to 4,500 calories. So a massive amount of extra calories being consumed that they added via sucrose or glucose, and they did add some fat as well. And then they compare that to an energy balance treatment that controls in 8 lean and 5 obese women. So this is the general protocol, 96 hours, which is 4 days of massive overfeeding using primarily sucrose or glucose. Of course, again, sucrose has the fructose in there. And they compared that to a control group that didn't have any increase in overfeeding, any increase in calories. There was some fat provided in the overfeeding, And the way they did this was using sugar-sweetened beverages. So they basically used an equivalent of a soda, cola, that either was made with pure glucose or sucrose. Now, this is, if we were ever going to see excess de novo lipogenesis in a group, it would be the group consuming the sugar-sweetened beverages, which is the exact villain that Lustig is often discussing. It's, at the end of his Sugar the Bitter Truth talk and many of his others, he's advocating for attacks on sugar-sweetened beverages. This is the culprit here that he is pointing to. We're not discussing whole food forms. We're not discussing, eating fruit or something like that. This is what we would expect to be the worst of the worst, 50% overfeeding using sugar-sweetened beverages. Now, again, as I mentioned earlier, we can't really effectively look at pure fructose studies. It's still worth looking at them and saying that they're even then not even showing much in the way of de novo lipogenesis and uric acid and all of that. But we have to remember that pure fructose does not get well absorbed, so it then feeds bacteria, causes endotoxin production, which we know will cause issues at the liver. But in this case, we're looking at sucrose, which is far more relevant. And again, you're not getting pure fructose in your diet, so this is the one that's actually relevant to what people can eat. Now, what they found was that de novo lipogenesis was 2 to 3-fold higher after overfeeding by 50% than after the control treatment in all subjects. The type of carbohydrate overfeeding, sucrose or glucose, had no significant effect on de novo lipogenesis in either group. So there was an increase in fat production at the liver by 2 to 3-fold, which sounds like a lot, but we're actually only talking about a few grams here, so I'll get to that in a second. But there was an increase, but it was no different between sucrose and glucose in massive overfeeding of either of them. So we have a nail in the coffin right here. Now, again, just to touch on this, the de novo lipogenesis amount in the control group, the group that wasn't overfed, was estimated at about 1 to 2 grams, a couple of grams of fat being produced at the liver. Again, this isn't concerning. There's always fat going in and out of the fat stores. You're going to have fat release from the fat stores at the liver and from the body fat stores. So there's always a little bit that's going to be going into storage, a little bit leaving. But when they talk about, a 2 to 3-fold increase, the increase was really only up to about 3 to 5 grams. It wasn't a large increase in absolute values. It's only a couple grams. But of course, that is a lot in terms of a percentage. But again, not particularly concerning when we're talking about fat stores. And we have studies talking about how even in these massive overfeeding studies, the amount of de novo lipogenesis from the carbohydrate is only a fraction, normally about 1% of the amount of fat that's being consumed, which is much more likely to be stored as fat anyway. And we'll come back to that in a little bit. It's also worth mentioning that the amount of de novo lipogenesis increase was a little greater in the obese group. I don't believe it was statistically significant, but it was a little bit bigger there, which we would expect. When there's metabolic issues, that's when we're going to see a bit more de novo lipogenesis, as we discussed. We want to work on fixing those metabolic issues. They then conclude with this last quote stating, "The results of the present study show that overfeeding with mainly glucose or sucrose for 96 hours increased de novo lipogenesis to the same extent, which suggests that in the long term, the fructose component of sucrose ceases to have a strong lipogenic effect." And the reason why they're talking about the long term here is because there are other studies looking at, a few hours after consuming fructose, what happens. But this is looking at it over a longer term, which gives us a much better idea over 4 days straight with large amounts of fructose coming in, showing that it's not uniquely converting to fat or causing an inflammatory state at the liver, even in this case of massive overfeeding. Now, as I was saying, we do know that if there's dysfunction at the liver, let's say there is fatty liver disease present, and you're consuming a large amount of fructose, you will see more de novo lipogenesis than glucose, because more of it does go to the liver. But it's important to be clear here that that's not because the fructose is causing this issue. It's not because it caused the inflammatory state at the liver. It's not because it's interfering with mitochondrial respiration and preventing it from producing energy using the fructose. It's because the liver is already inflamed and damaged, which is reversible, by the way. And even in this case, where you're having this liver dysfunction, it's not the fructose that is primarily responsible for the fat production. Even in these cases, free fatty acids are far more responsible. These are the primary substrate that are used to produce fat in the liver. And we'll go over a study on this in a little bit, showing that in the case of fatty liver disease, it's the fat that's actually being utilized to convert to fat, not the fructose or other carbohydrates. If you enjoyed that clip, you'll definitely want to download the free Energy Balance Food Guide. The Energy Balance Food Guide will help you determine exactly what to eat to optimally support your metabolism and help you lose weight, improve your digestion, get amazing sleep, boost your energy, and so much more. The food guide makes it extremely easy to get started with a bioenergetic approach to optimizing your health. So head over to jfeldmanwellness.com/guide to download your free energy balance food guide.